What you're watching is a high-speed pharmaceutical packaging line, processing white ointment tubes in a continuous blur of mechanical motion. On a contract manufacturing floor, this constant throughput creates a dangerous illusion of profitability. To accurately diagnose the health of a production run, we use manufacturing variance. Mathematically, this is simply the difference between the standard expected cost of production and the actual incurred cost. That standard cost is the absolute operational baseline. It sets the exact expectations for material usage, labor hours, and machine time required for accurate budgeting, forecasting, and pricing decisions. When actual costs eclipse that baseline, the resulting variance acts as a live diagnostic of operational failure, revealing exactly where time and money are bleeding out of the system. Without proper variance analytics, hidden bottlenecks and absorption issues remain completely unresolved, silently eroding a facility's EBITDA shift by shift. This waterfall chart illustrates a specific production example. We start with a baseline standard cost of $29,340, but by the end of the run, the actual cost jumps to $32,800. That leaves us with a $3,460 unfavorable delta. Executives need to know the exact operational failures that created this gap. To find out, we break that total variance down into its distinct mathematical components: material usage, labor efficiency, and absorption variance. Labor efficiency variance measures operational execution. We calculate it by taking the difference between the actual hours worked and the standard expected hours, then multiplying that difference by the standard labor rate. Absorption variance occurs when production volume falls short of expectations. With lower throughput, the facility fails to fully absorb its fixed overhead costs, leaving a costly gap in the ledger. The most dangerous hidden metric inside these gaps is idle capacity, which represents completely unused manufacturing runtime. If a single packaging line sits idle for 65 hours due to a scheduling delay, and the absorption rate is $50 an hour, that single delay generates over $3,200 in unabsorbed costs. Translating financial losses into specific operational realities is the first step, but computing these metrics across an entire enterprise requires structuring raw ERP data. Here we see the raw data required to calculate these variances. Inside SAP, it lives in highly fragmented, disconnected tables for production orders, costing data, and labor actuals. To extract and prep this information before it reaches the analytical model, we use Power Query as an automation engine. The first step in this automation is filtering out invalid or incomplete production orders, ensuring we only analyze legitimate runs. Next, establishing the baseline requires merging standard routing data directly into the production actuals based on matching SKUs. We then merge in the labor actuals and calculate the base runtimes to complete the data preparation phase. Rigorous automated data cleansing is a mandatory prerequisite. A variance model built on raw, unvalidated SAP exports will produce flawed conclusions. Once the data is clean, we have to architect it into a strict relational structure to allow for dynamic analysis. Poorly planned architecture results in a tangled schema full of circular dependencies, which destroys dashboard performance and slows calculation times to a crawl. This diagram illustrates a clean design, starting with central fact tables. These store the quantitative actuals, variances, and labor hours generated by daily production. Surrounding them are the dimension tables, which store descriptive attributes like product SKUs, manufacturing lines, and calendar dates. These dimension tables provide the crucial filter context needed to slice the variance data by specific products or specific time periods. This specific central topology guarantees rapid drill-through capabilities, allowing executives to query millions of rows instantly. A clean star schema is the structural bedrock required to transform disconnected daily data into a scalable, high-performance business intelligence engine. With the structure in place, we reach the final computational layer, where standard accounting math is translated into Power BI's data analysis expressions, or DAX. On the left is the standard accounting formula for labor efficiency variance. On the right, we see its direct DAX equivalent, translating actual hours, and standard rates into code. Similarly, we translate unabsorbed overhead by defining idle capacity cost as idle hours multiplied by the absorption rate. Because of the star schema's filter context, this single line of DAX code calculates variance perfectly, whether you are viewing a year-to-date total or a single overnight shift. To push this further, we introduce disconnected parameter tables for scenario modeling, which allows executives to stress test their operational assumptions. By adjusting a parameter like labor inflation, the new percentage automatically cascades through the DAX measures to show the projected impact on EBITDA. DAX elevates static accounting rules into a predictive financial engine capable of forecasting future risk based on operational variables. This is the final executive dashboard, aggregating the Power Query, Star Schema, and DAX layers into a single pane of glass. Executives rely on these high-level KPI cards to spot deteriorating EBITDA trends the moment they begin. Using the drill-through workflow, a user can click an unfavorable material variance and immediately isolate the specific SKU or customer driving that financial loss. This visibility exposes a core strategic trade-off. Increasing customer responsiveness often requires sudden schedule changes that disrupt manufacturing sequencing. While those schedule changes may appease demanding clients, they directly generate idle labor, lower overhead absorption, and severe operational instability. Building a rigorous mathematical variance analytics system is the mandatory first step before any facility can deploy advanced forecasting or enterprise AI platforms.